Okay, I'm going to take you through just a couple slides on what titration is, do a couple problems, then I'm going to, so you guys can get working on this case that we created. Okay, so let's just talk a little bit about the theory behind titration. In a titration, you're reacting a strong acid like hydrochloric or nitric acid with a strong base. Well, there's actually many types of titrations, but the simplest is a strong acid and a strong base titration. And in that, you're going to create a salt. And by salt in chemistry, we're very general. We just mean an ionic compound. So when we think of salt, or maybe when you think of only sodium chloride, but potassium nitrate is also salt because it's ionic compound. So you create a salt and water. So easy sort of mnemonic or whatever. An acid and a base creates salt. Remember, just a general ionic compound, and water. I'm going to write out the net ionic equation in a second, but I want you to think about what that net ionic equation is going to be conceptually, because think about what we're doing here. If we react all of our strong acid with just the right amount of strong base, our products are going to be entirely water, which is pH neutral, pH 7, and a salt, which really doesn't contribute to the pH at all. So the whole idea of a titration, which I'll get to in the next slide, is to try to figure out here. Actually, let's go to this next slide. The whole idea of a titration is to find the unknown molarity of an acid or base by finding the precise volume of the opposite chemical and reacting that opposite chemical so you consume all of that unknown acid or unknown base. So I'm going to show you a video of it in a second. Like you can see here, it's not the most exciting video, but just a couple of things. So here's your Erlenmeyer flask. In the flask, we're going to have a known amount of, I think in this video, it's a known amount of acid. We're going to put an indicator in here, and the indicator is going to tell us when the solution goes from acidic to basic, which is basically when it's going to be pH neutral. And then we're going to add something with really precise volumes. This thing is called a burette, and the burette is really designed to give us an exact, precise amount of volume that we're adding into our, in this case, in our acid. So in this burette, I think in this video, the acid is hydrochloric acid. They put an indicator called phenolphthalein in it. And then in this burette, they have a base, it's sodium hydroxide. So in this video, you're going to see them add just the right amount of base to this acid so that the acid and the base react completely. So there's no excess acid or no excess base. The only thing that's going to be left over in this flask is going to be salt water, right? So it's a kind of an interesting bit of chemistry. We have this incredibly powerful acid, which I would not recommend drinking. This incredibly powerful base, which again, I would not recommend drinking. But if we react them in just the perfect ratio, we have these very reactive products, and we form these very stable, we have these very reactive reactants of the base and the acid, and we form these very stable products. So if we did this just right, all that would be left in this flask would be salt water. So it would be essentially drinkable, right? All right, so let me show you this video. I'm going to do it at double speed because it's kind of boring, but I just wanted you to see the mechanics of titration since we're going to be doing a couple things with it. All right, let's make this big here. All right, I'm going to double speed it. So it's going to juice up this nice calm music. All right, so just a couple things. So they're going to put 25 mils of hydrochloric acid. They don't know the concentration, right? That's what they're trying to find. They're using a tool called a pipette to do this, and pipettes are just, again, giving you very precise volume. So what we want here is a very precise amount of the unknown acid, exactly 25 mils, 25%. This is an indicator called phenolphthalein. Phenolphthalein is clear in acid, but it turns pink in the presence of base. So when we have just the right amount of base to neutralize the acid we have in our flask, it's going to turn pink. This is our base, right? So we know the concentration of the base, and we're going to pour that in the top of our flask. And now here's the titration piece. So they're slowly adding this base, and then as they're adding it, this is turning pink. When this pink color stays, that's when they know they added the right amount of base, right? So we know that we can actually measure the amount of base we add using that burette. So here we go. Add. I might actually skip ahead because nothing really happened here. Okay. So after a while, she's added a bunch of base. Now see what happens at this sort of magical point, which we call the end point. Come on. Okay, so then we see the colors lingering longer. We're close and close to the end point. And then there you go. So now that it stayed pink, now we're going to look at our burette. I don't know, let's see if they do this. Yeah. So now they can look at their burette and they can see that they've added just this amount of base. So now think about what we have here. We have a known concentration of base, is 0.1 molar NaOH. We have the volume of that, and we added that volume to an acid. We don't know the concentration, but we know the volume of the acid. So using those different measurements, we can find the concentration of our unknown acid. Okay. I think now I want to sort of kick it into a couple problems, but this is a formula that we're going to use. So the sort of the key to titration is that at that point when that solution turned pink, what we're assuming is that the moles of acid equals the moles of base. We can rewrite moles using molarity times volume. Molarity times volume equals moles. So this is just sort of a fancy way of saying moles of acid equals moles of base, but we can plug in all the things we know. We know the molarity of the base that was in our burette. We know the volume of the base that we added, so we know molarity in B. We know the volume of acid that's in our Erlenmeyer flask here, and then we can use that to solve for the unknown molarity of the acid. Pretty straightforward calculation. Okay, I'm going to flip it over to my document cam so I can go over a couple different titration calculations now that All right, let's see here. All right, so let's start off with that first. Here we go. Let's start off with that first question. What is our net ionic when we look at an acid-base neutralization reaction? Let's take this top one here. Remember, net ionics, we get rid of anything that's aqueous. Really, we get rid of anything that didn't change, right? So we have on this side, we have hydrochloric acid and sodium hydroxide. Remember, this is a strong acid, so that means it's going to fully dissociate. This is a strong base, that means this is going to fully dissociate. This is aqueous, that means it is dissociated, meaning it doesn't form precipitate. And this is a liquid water, so we don't break that apart. So now if we look at sort of what has changed, right? We have sodium ions on both sides. We have chloride ions on both sides. So what's left? We have an acidic proton, a basic hydroxide, and we have water. So if we write that all out, what is our net ionic equation? It's aqueous H pluses react with aqueous hydroxides to form liquid water, right? So if you see this here, it may be a little bit clearer why these work. All we're doing is we're trying to react all the protons with all the hydroxides to create just water. When our titration's done, we essentially want none of these reactants left, and we want all product. And remember, that means it's going to form something that is pH neutral. So then we can use this sort of idea to figure out, if we know how much of this we have, we can figure out how much of that we need to add, or vice versa. All right, let's look at a couple of different calculations here. Let's see this first one here. All right, so the titration reveals that 11.6 mils of a 3 molar nitric acid are required to neutralize the sodium hydroxide in 25 mils. What is the molarity of the sodium hydroxide? All right, so we have sodium hydroxide in here, and we know, sorry, you can see that there. All right, we have sodium hydroxide in there. We measured it exactly, 25.0 mils. We always have a lot of sig figs when we use titration because it's a very precise technique. What else do we know about it? Okay, so what are we trying to find out? What is a molarity? So we're trying to figure out that molarity of our unknown. All right, so it doesn't say here, but we added an indicator. In this case, if you add the phenolphthalein, this is actually going to start off pink, and then when you add the acid, it's going to turn clear. So the opposite of what you saw in the video, but that's fine. You can always go from clear to pink or pink to clear. It doesn't really matter. All right, so then it said in our burette, we had nitric acid. So this is our nitric acid here. Let me write that lower so you can actually see it. Okay. And it says we use 11.6 mils. So after we were done, let's say this is 11.6, we could actually measure it. 11.6 mils of this acid were added. So again, what that's saying is it took exactly 11.6 mils of our nitric acid to react all the hydroxides that we had in this 25 mils. Once the titration's done, this should be pH neutral, or pH 7, right? Because all the hydroxides had reacted with all the acids. So the actual calculation is pretty straightforward. We're trying to find the molarity of our base, right? So the molarity of our acid, let's see, we know it. Oh, it's 3.0. So our molarity of acid is 3.0 molar. Remember, molar is moles per liter. So we want to put our volume of our acid, we want to put that in liters. It's 11.6 mils. So 1, 2, 3, that's 0.0116 liters. and that's going to equal the molarity of our base, which is, that's what we're trying to find out, right? So we'll just write molarity there. And we know the volume, we have 0.02500. And again, all these zeros are here for sig figs because titration is all about really precision. All right, so if we do this out, we divide both sides by 0.025. We get our molarity of our base. So 3 times 0.0116 divided by 0.025 gives us 1.3. How many sig figs do we have? We only have 3 molar there. So 1.39 equals 1.4 molar. And just kind of think about that number, make sure it makes sense, common sense check, right? I had 25 mils of base. I needed 11.6 mil of 3 molar acid to neutralize it. So since I have more base than I have acid, that means the molarity of my base has to be less, right? You can think about this other question. If it took 25 mils of a 3 molar to neutralize this, right? So in other words, if the volumes were equal, then the molarities would have to be equal, right? So the fact that I had to use less volume of acid than I had base in my flask tells me that the acid has to be more concentrated in order for that titration to work. And again, sort of the whole thing, right? Just so we are clear about this, I'll just write this down here. The whole assumption here is that when our indicator changes color, moles of acid equal moles of base, right? And if we go back to our unit on solutions, we have molarity equals moles over volume. So if I write, I can also solve that for moles. Moles times volume, same thing, right? All I did was multiply both sides by volume. So then again, if I write MV of acid equals MV of base. So that's where this formula comes from. It's a pretty simple derivation. The other thing too is this formula only works if you have a 1-to-1 ratio. It still could work if you had a 2-to-1 ratio. Let's say a sulfuric acid, which is diprotic, so it contributes 2 protons instead of just 1. Then all you have to do is put a 2 in front of besides. I don't want to get into the whole thing with that, but in case you're wondering, like, does this work for acids that aren't monoprotic, meaning only contributes 1 proton? Yeah, the formula works. You can also just use kind of same stoichiometry too, which is kind of what this is based on. All right, one more problem. Titration reveals that 50 mils of a 0.1 molar sodium hydroxide are required to neutralize 25 mils of hydrochloric acid. What is the molarity of the hydrochloric acid solution? All right, so here we go. Let's just kind of figure out all our numbers. 50 mils of a 0.10 molar sodium hydroxide. So our volume of our base is 0.0500. How many zeros? Lots of zeros. It actually doesn't matter because we only have 2 sig figs with a molarity. I'm just picking these right from our problems. Neutralize 25 mils of hydrochloric acid. So we know our volume of our hydrochloric acid is 0.025 mils, or 0.025 liters, sorry. So we're looking for that unknown molarity. So if we do this all out, we get 0.10 times 0.050. I'm just kind of being quicker with the sig figs since we don't need to take that many anyway. All right, so you actually could probably figure out what this is going to be just based on these numbers, but I'll run through the calculation. So 0.1 times 0.05 divided by 0.025 equals 0.2 molar. So just think about why this number makes sense, right? We had 50 mils of sodium hydroxide, and we added that to 25 mils of acid to neutralize it. So it's twice the volume of the sodium hydroxide, right? So that means if we added twice the volume to neutralize the acid, that means the acid had to be twice as concentrated as the base. So if our base was 0.1 molar, that means that acid should be 0.2 molar, which is why the acid needs twice or half the volume of the base, right? If they're the same concentration, then the volumes would be identical. Anyway, hopefully that gives you some background and sort of how titration works, and then you're going to use this knowledge to do a little case.